appear accordingly. Now the question is, we can always try to identify this using neural networks as well, and that is because neural networks are typically function approximators as well. And we all know that neural networks can also be represented in, I mean, used from pattern recognition point of view, and there are tons of applications for that, right? From I mean, bio identification to fingerprint identification, signature recognition, text recognition, it doesn't stop anywhere, correct? And in the control theory of perspective as well, we also started using it a lot of pattern recognition business. The reason being, a lot of our applications are actually governed by external sources also. For example, you are flying an UAV and then suddenly something problem is there, you want to find a landing area basically, right? So how do you do that? You can open up your cameras and look at below and then see, oh, this possibly looks like a flat land or maybe highway or something like that. So can I really align myself and land there? So what you are talking about is not really a control system per se, but augmented information or rather very critical information that is required for control system to operate. And then a lot of examples. I mean, you can, so those of you who are working on robotics will find it immediately correlate that. I mean, even ground robotics also, the perception basically, right? If you really talk about a robot which can be like, let's say, geriatric tray. So it is one of the applications that is close to my heart. Can we really talk about a wheelchair with all sort of cameras involved? I mean, maybe something on the back side, something front side, all sort of things. And can we really talk about cheap sensors? Let's say, I mean, it's a very cheap sensors, you can put it there, and then it will figure it out, some obstacle avoidance and things like that. Okay? But that is actually not really independent of control system. In other words, that information will be very much really required for your robot or for your rather smart wheelchair to operate. Right? It has to figure it out from living room to drawing room. I mean, from living room to bedroom to whatever it is you want to go, basically. Right? So that kind of things are very much essential for the overall system perspective. Control system, the traditional way is certainly needed, but what is really needed is actually so-called this artificial intelligence business, right? You want to make your control system little more smart, little more intelligent, little more things, right? So from that point of view, you really need a lot of perceptions actually. I mean, that is perception also, remember, it may not be static, it happens to be dynamic. In other words, a lot of emphasis is there towards video processing now. But even before you go for video processing, there is something called image processing. And that image processing is a little too much for doing in real time because in control system has to operate in real time, right? And you want to go now, basically, right? That you don't want to wait there and then figure it out what is the living room to bedroom and then go. It's not that way. Right? So many things are there, which requires little external information about and this artificial intelligence. And one of the techniques that happens in artificial intelligence happens to be through neural network, obviously. And the neural network has gone leaps and bounds over a period of last decade sort of thing from its beginning. I mean, the beginning has been can be traced to very far, but what I'm talking about is so-called deep neural network. So traditional neural network has its own limitations, so you cannot go more than 2-3 layers and things like that. But now people talk about massive neural networks and all that. Even then, I mean, you really talk about some degree of intelligence in the sense, sorry, some degree of intelligence in the sense whatever image processing techniques are available from image processing theory, then can you really not bring in and then give some sort of intelligence to these neural networks and all. In other words, you really don't want to do image processing online, basically, right? You can train your neural networks in such a way that that will I mean, very quickly you can figure it out what is really happening by using those neural networks. So this with this introduction, this talk is going to be more or less exposure to a kind of a tutorial exposure. It is not really advanced thing. It is you can interpret that as a very little pedagogy. I mean, this small concepts building up from starting from the scratch. So, what is neural network? What is a traditional? Back propagation training and things like that, and then slowly building up towards exposing you halfway through. So, this deep neural network. And what is really going on there? Why this deep neural network has become so much popular? And deep neural network, when you talk about DNN, one of the architecture that is very popular is something called CNN, that convolutional neural networks, which is predominantly used for image processing. So again, I mean, this particular topic is very much augmented to the control system in the very outer look. In other words, suppose you have to drive your vehicle or robot or car or even that smart wheelchair, you don't need all sort of things, right? So then what is really happening? Your perception thing, your eyes, ears, and things like that, is generating that information and eventually driving that little wheelchair or robot or even autonomous cars and all that. Right? That's also robot by the way. So those are the, with those motivations intact, we'll go through this this lecture and try to understand a little bit deeper into that, with little bit deep dive, because many of the talks that you typically listen elsewhere will not expose you to this tutorial sort of ideas in my belief actually. All right, so go through that. I mean, this is actually a kind of a pre-recorded video. It has been shared with Professor Abdul Kumar. So I'll be there. I will be there at the end. I will come back and try to explain, or rather, try to address some of your questions, concerns, if you have anything. So with this introduction, let us get started with the actual one. Thank you.
Okay, sir.
You can get it done, right? Isn't it? I don't have to do it, isn't it? Just make sure to share the audio also when you share it. Actually. Are you doing it?
Yes, sir. Yes, sir.
You can probably play and share your screen, and then while sharing, you have to opt for this include computer sound and all that, right? That one.
Yes, sir. Yes.
What you see is the main building of the institute. The institute is pretty big.
Probably you can start from the beginning.
What you department? So those are those motivations in that.
Audio is not good. I think you should start from the beginning.
What you see
You
is
can start from the beginning. It's not listening properly.
but the institute is pretty big. We've got about 500 acres land. We've got 40 departments and centers. So we've got 4,000 students, 500 professors, 2,500 publications per year. IISc are the number one in India in research performance. So this is a nutshell of the my institute where I work. More on that you can probably see in the institute website.
Well, don't keep changing all this. Just keep it there.
So this is, if you happen to come to my lab, you'll see the works on various things. We are interested in several aerospace applications, of course. So we do research on missile guidance. We do have bio-inspired navigation and guidance. And missile guidance means all sort of things: surface to surface, surface to air to air, all sort of persons. And then we got space applications like formation flying of satellites. That's where one book is getting published pretty soon. And then we have soft lunar landing. We got interest in that as well. Of course, there are some activities on UAV related stuff. And we are also interested in high performance aircrafts, also with reusable launch vehicles, hypersonic flight vehicles. Many of these things are aerospace. We are also interested in biomedical applications, and one main activity in our lab happens to be the automatic drug delivery, especially with respect to insulin delivery for type 1 diabetes. Then we are also interested in several other applications like the brain control activities for eye movement, for example, or optimal process control, for example, this directed energy weapon for high energy laser beams. So there are several applications that we are interested in. Many of these will actually work around the control theory part of it. And as part of it, we also work on neuro control, neural network based control systems. So that is where my interest comes here to the neural network side of it. All right, moving on. This is the nutshell of my research interest. We do research on theory as well as applications. And as I told, most of our applications will be like aerospace engineering, guidance and control. However, we also work in a lot of theoretical aspects that comes out of these application problems, and that includes nonlinear control, optimal control, adaptive control, state estimation, things like that. So optimal control, adaptive control, that is where the neural network application comes in, and that is how we are interested in getting into the neural network domain. All right, so this is what I was speaking about. Control theory and neuroscience together leads to this neural control, and that is where neural network happens to be one of the key techniques in our lab for solving problems and designing new theories as well. So let's get started. So what is the difference between perceptrons and multi-neural networks? So perceptrons are nothing but networks with no hidden layer. That's called perceptrons. Of course, they are very limited in what they can represent, but makes the learning problem much simpler. Right? So obviously very easy to understand this. What is multi-layer? Just extending that concept. So you've got one or more layers of hidden units, and possibly very large hidden layers as well, and possible to implement any function. So this is just generalization of the perceptron. So this is the concept of a multi-layer feed-forward network. You've got you've got one output from a perceptron. Now you can talk about several outputs coming from that using different multiple things. Then you can connect back two layers like that, and then you can keep on connecting back many layers like that. So all these things is there in almost all standard textbooks. And one of my favorite textbooks in neural network, conventional neural network, happens to be this one. This is, I mean, this was a kind of my textbook also when I was a student as well. So they're very nicely written concepts in my view. So those of you are first time into neural networks, probably I recommend this book as well. Okay, so what is this generic feed-forward neural networks then? So this is what we saw, that multi-layer feedback feed-forward network possible. So how do you represent mathematically then? Right? So this is this mathematical representation of feed-forward neural networks. Remember, we have got this input layer, so-called just numbers coming from your data or coming from whatever you do. These are the input data information. Now we connect it to the first layer. So you just multiply with those weights and then take the summation, add a bias, and then talk about the summation that whatever output comes through that process, and then pass it to a nonlinear function, and you get output. Right? But does it stop there? It doesn't have to stop there, right? Because now these things what I see here, A11, A12, things like that, I can interpret them as an input themselves. Right? So I can actually feed that input to another layer. This is called, probably the second layer. And I'll do the same process, identically same process. I'll consider these guys as input to the second layer, and I will feed them with a different set of weights. And these are everything connected to everything, right? Every output is connected to every neuron. And then you'll get every layer will get weights, biases everywhere, and then again you'll get the summation process or whatever you get there, and then you get the output from that layer. Now just see what is happening. So now with this background, let us talk about some training methods. What are the training methods possible? And then this is a lot of neurons here. So this P itself is a bias vector. So training methods, learning procedures basically of different classes. And so you talk about W1 supervised class V1, and then get into some sort of F1. Everything is kind of so supervised learning is like a teacher teaching a student regularly. Initially you get A1, you really feed the network with what is, so that is the output of the first level. Now you consider that second layer, that's the output given the process. Now you see that this entire thing what you see here is now getting that information to the network, and then a similar thing. This is just selection biases plus some biasing, and then again supervised. So that's what happens. Unsupervised learning is completely unsupervised. It doesn't, you don't feed anything. Then eventually you have to keep somewhere. You consider, okay, my third layer also, which will try to explore itself, and that happens through the so-called self-free, whatever I see is my output of the. So this governance network, that is what the generic role and all networks are designed and used. So that is this association gets. So I hope it is conceptual. Your weights will be a function of the input, correlation between two data and things like that. Okay? If there is a correlation between two data, then the corresponding weights will become a little bit increased and all that. Right? That kind of learning you can do in the unsupervised learning world. So in between these two, there is something called reinforcement learning, extremely popular and extremely powerful. Basically, this reinvented now. It is having a lot of potential uses in the real robotics world. Basically. So that's called reinforcement learning. So essentially, what happens? Users give a little bit of information, whether you have done the job right or not. Okay? And that kind of generating that kind of data is much easier than generating the data for supervised learning. Because supervised learning, you actually tell what it has to do every point of time. Right? But here it is not required. Once a while, you can tell the robot or tell the network that, okay, you have done a good job or not done a good job. If you have done a good job, your corresponding weights will increase. If you have not done a good job, then probably the weights will increase. That kind of thing. So this is, I typically call, okay, when you have a PhD student, initially we have got coursework and things like that. So he goes through some sort of a supervised learning process for about a year or something. So once the coursework is over, then there is this reinforcement learning phase during the research period essentially. Once a while you will have these research meetings and things like that, where you think, okay, this thing is wrong, right, and things like that. On daily basis, you are not able to. Daily basis, you are not supposed to talk to the student and handhold him, and then derive everything, and then give the coding and things like that. So that's not possible there. It's not required also. And towards the end, the student becomes highly expert, and is supposed to be a better expert than the advisor himself. And so that is where the unsupervised learning kicks in, basically. Right? So the advisor doesn't have to be there in the picture at all. But the training process is pretty good, so you can figure it out himself what is good or what's bad. So this is kind of correlated to that as well. So reinforcement, this is with a teacher. This is kind of with a teacher, but later on not. And unsupervised is nothing, no teacher is all. So supervised learning, I've explained the concept already. So you got an environment and there is a teacher associated with that. Actually, it keeps on telling this is right, learn it. This is not right, don't learn it. So this kind of process keeps on happening, and eventually the learning system tries to kind of run it. Okay. So if there is an adequate set of training, adequate set of input-output data is there, then obviously it is trying to learn it. And it also requires enough time as well. So every learning process takes a lot of time. The learning doesn't become instantaneous. It takes a time. So repeatedly tries to correct the errors, and then over a period of time it tries to learn. So what is the supervised learning examples? Pattern and speech recognition, information retrieval from a database, things like that. And then you talk about, well, limitations. There are several limitations as well. First of all, you require the presence of a teacher. Without teacher, there is no learning. And then necessary to train the network beforehand. And of course, the reliability of the teacher itself is a concern. Like if you really feed the wrong input-output data, the network will pick up the wrong thing. The teacher tells something wrong, then obviously the student tend to pick it up. Right? So that kind of problem does happen here. And noise in the output values can spoil the training process as well. Okay? So these are some of the limitations as well. Okay? So moving on to reinforcement learning, as I told, every data is every input-output data is not fed. But it is presence of a teacher is there, but only right or wrong indication it will be there, right? So many of the times, this is pretty easy to generate a data, right? So if you talk about, like, let's say there is a gaming application, you leave the robot to game and things like that. As long as it does not hit anybody, then probably you can keep on playing. The moment it hits someone, you tell, okay, well, this is a wrong move, basically, right? So that kind of thing is pretty easy because sensor will pick up some sort of a collision happened and all that, right? So that kind of a process is actually easier to do. Okay? But the people also tell this very natural to do because let's say some child is born, the way he or she starts walking, initially it kind of falls down many times, but then from that falling down, it kind of learns and then stabilizes himself or herself, right? So that kind of process is available. That kind of things are possible. Okay? And this field again is getting a huge impact in the robotics world. Because it is that relevant. So learning is predominantly based on the feedback from the environment, but that feedback is sparse. It is not really very rich feedback. So the sparse information and a little bit of information, how do we actually learn over the period of time what needs to be done? Because that happens, that comes through because whatever is not declared as wrong, it is actually happens to be right. And whatever happens to be declared as right, you are double sure that it is right. So that kind of process, you can come up with some learning rules and all that. Now people talk about a lot of this probabilistic learning approach and all that. Many using dynamic programming, using several learning theories, and like that, where this field is getting a lot of impact basically on the real world problems. So that is where I think those of you who want to get into that, probably I strongly encourage this. All right, so this is one. Then unsupervised learning, obviously, is nothing supervised. The objective is to discover the patterns or features by itself and then no help from a teacher at all, not even occasional feedback. And the systems develop its own encoded patterns and typically use self-learning rules. And for example, one famous thing is the Hebb's rule. So this is what you can feed a bunch of things, and then it tries to kind of do some, kind of throws this side, that side, and all sort of things. In other words, if I happen to see the red color, if I happen to see some sort of a yellow color or something, and then something else, and things like that. Right? So try to kind of classify. Oh, this looks like all red, so this must be something, and this looks like all yellow, something. So that is kind of a learning rule that keeps coming from so-called Hebb's rule. So this is good in some sense, but it has not matured to a level that people can actually use confidently. So what happens to be a somewhat middle ground, which is actually the reinforcement. So all right, so coming to the limitations of unsupervised learning, of course it has computational complexity, it is unreliable output for out of domain data. So the right, obviously, and then external control. No external control on the error as well. And again, examples are many. You can talk about modeling the relationship between clusters, reducing dimensionality of high-dimensional data, and things like that. So again, if you really want to summarize the classification of learning algorithms, it turns out that there are many things that are possible. We got supervised learning. There are several things. Error correction gradient. There are stochastic things that is coming into picture now, very big way. And that is particle swarm optimization, this genetic algorithms, simulative learning, they are all kind of stochastic domain. And otherwise, this error correction gradient descent part of it, I've got least mean square, back propagation, things like that. Similarly, unsupervised learning, we've got Hebbian learning, and then there's this computative networks, and then computative resonance theory they call, things like that. And then reinforcement learning. So this is essentially output based. So there can various lot of training rules are possible. And people like us, control theory point of view, we can also come up with Lyapunov stability theory based learning techniques, which is the stability theory based learning. So what we do here is we'll give emphasis to this back propagation. So that is what is used in the feed-forward network, and then that is actually used in the CNN network, and deep networks also. So with that motivation in mind, we'll give some importance to back propagation. All right. So now moving on, what is the philosophy more than names? So what is the idea here? We have this feed-forward network where the data is there. We pass it through forward cells and get some output. But this output is not really the output. We got the input, we pass through several layers, got some output the way we have seen it before. But obviously that output is garbage, right? It really doesn't kind of capture the data at all. So our real data can be something else, basically, right? So how do you kind of make sure that the next time you put that, then that actually predicts the property? So in other words, if you consider the real data, the target data essentially, as the true data, then whatever the output data that is coming out of the neural network as the output of the network essentially. Right? So this output of the network with respect to whatever weights it already has, and then if you take the difference of that with respect to the real data, that is error. Okay? So that error needs to be minimized. That's all it's. Okay? You take the real output from the actual weights, whatever is there from the neural network, but there is a target data. So there is a difference between that, and that difference needs to be minimized. Okay? So essentially, it leads to a minimization problem. So what it tells you that okay, there is a forward part, so forward step because the network activation forward step, and then there has to be a backward step where utilizing this error, all these weights in the previous layer has to be optimized or adjusted or updated. Okay? So that kind of thing, that idea is called back propagation. That operation. First is forward propagation, forward operation. Then there is a backward operation, back propagation. Okay. So this is what we want to do here. So what do you do it here? Remember, this is what happened, right? Input, and first layer, second layer, third layer, output. This is the formula that you've seen something. Now the whole idea is this is the actual output for whatever initial weights I have or whatever intermediate weights I have. That is nothing to do with the real target weight. So let's denote the target weight as something else. Now let us call this A, whatever you talk about. Instead of A3, we'll call that as A for simplicity part of it, because that's the final output. So we'll redefine the error as something as output as A, whereas the actual target is something like T, and the error between them is A and T. Remember, all these are vector variables now. B is a vector also. Okay. So what you want to do, you want to minimize this E by constructing this function, basically J of X. But what is X basically, right? The question is what is X? and X is nothing but weights and biases. So that's the only thing that you can really adjust here, right? The actual input are coming from your experiment or whatever you are having from sensors or whatever it is that you cannot have a control. The only control that you can do is your weights and biases. So that your X what you are talking here is not the input, but essentially weights and biases taken together. Okay. So you minimize this error function J with respect to weights and biases. That's what you want to do. And eventually you will come up with this kind of a very rudimentary control, kind of update rules, taking the help of the steepest descent gradient algorithm. Right? If you happen to take advantage of steepest descent algorithm, then this is what you will come up with. I've got a weight and bias, which I will take a gradient of that function with respect to the adjustable parameters, and I talk about updating that by taking a small step. That is a learning factor alpha. So that is all about weight propagation. Now the question is, these weights, remember, they appear within a function, within a function, within a function, right? So, you know, these weights appear like function of a function of a function. So how do you handle that, this partial derivative here? Now, this partial derivative has to talk about all sort of possible weights. It will talk about W3 adjustment, W2 adjustment, W1 adjustment, similarly V1, V2, V3 adjustment also, at one go. Okay? So how do you do that? That is where the chain rule of derivative comes in. And that is what you will utilize some of the chain rules that we discussed before. Again, I'm not going to talk in detail, but that's the whole concept, whole idea of it. Okay. And remember, these back propagation algorithms and all that are pretty much standard. You can even in MATLAB, you can talk about neural network toolbox, and the toolbox has a standard algorithm for this, utilizing this LM algorithm, Levenberg from algorithm. And there are other things. There are programs available in Python, C, also. So what is the improvements you talk about? Well, you can think about conjugate gradient method in this instead of simply using the steepest descent, or you can even think about Levenberg method. And that is the very default algorithm happens to be LM algorithm. So that's the whole idea of back propagation. It feels simple, but remember it was a major bottleneck in the timeline of this. So basic idea, as I told, is not really very different to see. Instead of just having one or two hidden layers, now you've got many hidden layers. So many layer neural network architecture should be capable of learning the true underlying feature, and this feature logic is validated after that. And therefore, the idea is such a network is supposed to generalize very well. Right? So that's our idea there. So now the question is, does it happen or not, or things like that. So let us see that part of it. And what are the difficulties? So again, the motivation is, well, machine learning in practice, a large part of the exercise happen to be human-centric, right? Domain-specific knowledge, and very good experts are needed to tell what are the features that you're looking for this particular class of things. And that is what sometimes people call it requires PhD level talent, very good domain expertise. And then the optimizing and waiting on the features are learning algorithm. After you do that part of it in a hard way, this part was relatively simple. Right? But that is what you want to combine. The traditional machine learning methods work because of the human presentation and input cases. So that is what, in a way, machine learning becomes just an optimization of weights, and probably that is not what machine learning is all about. Right? It should do both the things. Right? It should not be only optimizing the weights, but it should also identify the features in a good way, especially in the context of image processing. So the question again turns out to be like summary sense. The question is, can something be done to make the process more powerful so that the domain-specific knowledge requirement is eliminated? Right? That's the bottom line that you're talking about. Again, what is deep learning? If we talk about that, so machine learning is kind of a subfield of a learning representation of data, and well, you can read some of that. Essentially, what it means. If you give a lot of information, right? Suppose you give the system tons of information, then is it not capable of understanding and respond in a useful way without the feature extraction PhD level guy sitting out there, right? So this machine learning has some intervention like that, but suppose this one we want to eliminate. So can this process be automated, right? So essentially, you talk about conventional neural networks with limited layers of hidden layers, so limited number of hidden layers. Then you need this this external support for that. But in a deep learning sense, we suddenly try to eliminate that and try to kind of let the network learn by itself. So obviously, you are talking about bringing in some sort of this feature extraction techniques that are studied well into the image processing literature, and then making that as part of the neural network learning process itself. Right? So that is what you are trying to do, and that is where you talk about a lot of these image processing filters. These are getting used in this study. And selection of these features, various permutation combination, everything will become part of the learning process. Now, leaving that aside, we will now get into the deep neural networks, which was the predominant motivation of this website. So the question is how exactly it is done. Okay, so that is where I will request all of you to kind of pay attention to the upcoming slides really carefully. This is the kind of relatively recent development. So what is convolutional neural network? So you take an input, typically in the form of image, and this we have got several hidden layers, and this can be as large as something like 24 by 24. Then the N1 can be in the third dimension, right? So that is we're talking about like that. Then several kind of layers it passes through, and eventually it is all stuck together like some sort of a plotted number sort of thing. And finally, there is a fully connected network, and this is where you apply your backpropagation and all that. The rest of the things you do image processing ideas basically. So here you can do some error classification and things like that, which which idea worked better, which idea did not work better, and that is where you can keep that the idea that works, discard the idea that doesn't work. You have to try several permutation combination, and eventually that process, whichever works better, will store that as a learned learned parameters of the neural network. So what are those things that you're talking about? The last thing is pretty simple. We have already talked about the backpropagation, and essentially it's going to be a large vector, and there is associated classification available, and that can be done using the standard backpropagation theories. Okay? So, and remember, if it is only the last layer, it talks about a linear in the weight neural network at that point of time. Right? If you forget everything else before that, and just concentrate on the only last part of it, you can rather do it relatively easy, because the weights typically may appear linearly depending on the activation function that we talked about. All right, so this is the concept. Now, what is the difficulty, right? So you know the remarkable improvement of this CNN or convolutional neural network can be attributed to some 3-4 big developments. So big development happened to be like 3D linear filters. So you talk about what are these filter essentially means this image processing techniques. So those are the things that are used for getting into the feature extraction part of it. That is inspired from the image processing techniques. And then there are this downsampling. Your original image can be pretty big, but you can talk about downsampling. You can only retain the important things, forget the rest of the things. And then there are this some concept called pooling, that essentially you don't carry forward everything. You can talk about either max pooling or average pooling and things like that. Each having their own beauty. And typically the most utilized thing is max pooling because of the good noise suppression characteristics. And then eventually you talk about a different activation function, which is called the rectified linear function. So it's essentially nothing but a linear line, but linear only in the positive axis, but zero in the other axis. There are reasons for that, and all that we'll talk about as we go. And there is a fourth. The last one is the different way that of this optimization process, which is stochastic gradient different, stochastic gradient optimization. So I'm not going to talk about that because that throws us to a very different domain altogether. But assuming that that part is kind of that part can be studied separately, we'll talk about some of these things which are innovation to the CNN architecture itself. All right. So continuing further, we'll see about these three things, okay, together, and the rally function we'll talk about it, studying it rather a little bit after that. Separately. All right. So let's get started. We'll talk about what is what is an image and how the filters are done and things like that. Many of these things I have taken from this particular kind of website, which is compiled a very nice way of, simpler way of understanding the concept. So now in general we'll talk about a colored image, which we know that it has got this red, blue, green sort of kind of classifications. And each of that, if we talk about 3 layers, and each of the layers will have all the pixels are characterized by intensity levels. Right? Red is how much intensity level, blue is how much intensity level, green is how much intensity level. And these intensity levels are classified with, I mean, they can be designated with some numbers. Right? So when I talk about 35, it is like 35 levels. So this is how it is characterized. Now the question is, you have to play around with all these numbers. Right. So once you play around with all these numbers, that idea is called image processing. And you do many things with that. You do this image enhancement, background enhancement, color enhancement, light enhancement. They are all the part of it. Right? Even the noise suppression part of it, the beautification. I mean, there are many things that are possible. Right? If your face is some couple of gray hairs, then using this video conferencing platform that I'm currently using. So some of these layers are suppressed also. They are considered as noise, and then your face will look beautiful. So many interesting things do happen in the image processing board. So let's talk about that. The first thing is, what is a convolution operation? So that is where this convolutional neural networks has come into picture. So first thing we need to understand is what is a convolution operation. Now you consider, okay, let's talk about one particular pixel grid sort of thing. And you consider this particular small thing out here, and then you consider these numbers P1, P2, P3 is correspond to this pixel intensity, something like that. Right? Now what you do is you take some sort of a filter, which is nothing but a piece of well, you can imagine as a different image sort of thing. So you talk about some sort of a small cutout image sort of thing, and that is associated with certain numbers. So this pixel is going to go and sit on that. And once this numbers of this 3x3 size sits on this 3x3 size again, then you have to do some algebraic manipulation, right? And this algebraic manipulation is defined as something very as simple as that. I mean, just take the inner product, right? In a vector sense. In a metric sense, you have to talk about it. So what it essentially means, you multiply A with P1, the corresponding value of A. This, remember, this is called a filter, and this filter is predefined size, and this predefined size are associated with prefixed numbers. You cannot change that number arbitrarily as you wish. So these prefix numbers is specifically meant for particular image processing. For example, you want to talk about intensity gradient, then you talk the finite difference formula you can bring in, and then you talk about some number here, some number here, some number here, so that it can do a x-axis differentiation. Similarly, if you talk about integration, then you talk about like multiplication and sum it up and add it up and things like that. So they are these filters are designed with a specific operation in mind, basically. Now, assuming that this A, B, C, D, E, F, G, I mean, all these numbers are available, but taking a particular filter, I'll just take it and drop it on this particular P1 to P9, that cell. Then what is my output? Output is going to be just one number. Okay? And that one number happens to be just H of Ij, and H of Ij is given like this. Okay? So I will talk about A times P1 plus B times P2 plus C times P3 like that, and everything I will just sum it up. Whatever number I get, that is my H of Ij. That's my output. So this is interestingly contains a lot of good information depending on what kind of a filter we are talking about. And that is what the image processing relies a lot on. This operation is called convolution operation. Okay, so if you talk about a single frame, it's like that. So eventually, when you talk about, well, if I take something like a filter of this particular thing, so this, okay, a filter of, let's say I talk about say 101 and things like that, I start operating from the very first one. Okay, just see that it is going to operate from first one. So it is first cell, second one second cell, third one third cell, fourth one fourth cell, like that. So it is the original image has been reduced to a very small size, essentially the same size as the kernel itself, the filter itself, and then eventually the convoluted feature happens to be like this. Right? Because for every filter, which we will talk about, taking the summation, everything will be summed over to a particular scalar value and dumped on the where it starts from, right? Where it acts on, actually. So that is how it is. The convoluted features are extracted like that. Remember, I hope I'm clear on that. So essentially, again, just look at this carefully. It starts operating from the very first one. It puts the first one, second one, third one, like that. Okay, depending on how many times you can do it and all that, without going outside the boundary of the image, that much size of the convoluted feature will come forward, right? So essentially, it is like if you scan through one dimension, you have to talk about -2 sort of thing. One side, one less from this side, one less from that side. So this thing happens to be 5 by 5. Now 5 minus 2 is 2. Sorry, 5 minus 2 is 3. So the output happens to be 3 by 3. So it's not because the filter size has become 3 by 3. It's not that way, right? The original image size, the number of pixels in one dimension, -2 becomes the dimension of the output particular. Similarly, the other dimension is the vertical dimension is well. Okay. So that is what it is. So that's the convolution operator. Now, what is RGB frame then? We talk about three different things. Obviously, you have to do three different things, and eventually it will talk about a kernel, and then you talk about, well, it eventually, you have to scale down to a particular thing, mixture of everything basically. Okay? We talk about red, blue, green, everything taken together. You get something a reduced dimension here, okay? And then again one more reduced dimension here, one more reduced dimension here, and then eventually sum it up and come up with a different output number. Okay. All right. So I hope it is clear on that. So this is what is happening here is this particular operator is getting operated on this particular size. This particular 3 by 3 cell basically. Okay. Once it operates on 3 by 3 cell, it kind of generates a number basically, and that now it comes to something from here, something from here, something from here. Add them all together and put a number there. Basically. So essentially, everything that is happening in red, blue, green eventually kind of gets reduced to a particular number. That's all. And beauty is, even though you are reducing it tremendously, you are still having kind of a lot of information along with that. So that is what is beautiful property. And that is what has enabled this technology quite a lot. So now people can talk about various things. You talk about, well, what we saw that is like one stride at a time. Now you can talk about two strides at a time. So that means you start with that. Don't go to the next one. Jump one and then go to the next one. Right? That's also possible. So quick swiping basically. So you don't have to keep on doing everything next to next to next, but you can actually do two things. You can skip one and then go to the next one, things like that. Right? So this is the stride length 1, which happens to be like that. What we saw before, this is stride length 2. You can operate with that way as well. Then there is a concept of padding. Okay, padding is essentially what happens. The resulting image happens to be reduced size. Yeah, I told you sometime before, right? Your two cells go from the two boundaries basically. But if you don't want to have that, then what you can do is you can just create artificial cells only for this operation, this convolution operation. And then eventually, whatever you do, the size of the resulting thing will not change. Size of the thing will remain same. And so that concept is called padding. And this normally what you do in this kind of artificial cells is just put zeros basically. So that's zero padding and all that. Okay. So after the convolution, it will retain the size of the image at least. It is not going to hamper the size basically. Okay. All right. So what is the problem of the convolution operation? The first convolution layer abstracts only the low level features. If you just do it one time, okay, the very large scale you can get it. Very kind of it's not a very sharp image. It's a kind of diffuse image sort of thing. Very large features you can get it. Probably get it something like a very big eye or mouth or something like that. But you'll not be able to find fine print actually, right? So the same mouth probably can be a tiger, can be a lion, can be a cat, can be whatever it is. Actually, you'll not be able to identify very properly. So if you talk about low level features, detailing basically, right? You talk about edges, you talk about corners, you talk about colors, and if you do all sort of things, then you probably need the support of many different layers. So what you do then? Now you talk about deep layers, and every layer you talk about something like convolution operation. So add layers, and that will kind of extract some high level features as well. So essentially, in a nutshell, what it means is the initial layers will talk about extracting the low level features, but you go to the deeper and deeper, the forward cells, the middle cells, and all that. The middle layers are going to extract finer features. Then there is this concept of pooling. This is purposefully done to reduce the dimension. And again, you are doing all this without kind of compromising on the output accuracy. You know that. Reducing that doesn't really mean that I am throwing many of this information. Not really so. So what you're doing here is, there is a concept of average pooling or max pooling. What is done? Suppose there is a 2 by 2, And if you really have to really see, it is like what I tell is like a lot of this flooring sort of thing. Like you see that there are tiles basically, right? Different dimensions and all that. So you take a large tile and then you kind of club everything to a small tile basically, right? So that, I mean, a lot of griddings are there. Now you kind of put it in bigger cells like that basically. So how do you do that basically, right? So when you talk with all these four things, you to consider that as a single cell. Then what number you are going to assign? All these four cells you consider as a single cell. Then what number you are going to assign? So that is the concept of where I will just talk. In one case, I will simply take out the maximum number, whatever maximum number is that, and this maximum number happens to be just 20 out here, right? So I will put that 20 to a reduced one cell. I'll talk that is 20 here. Similarly, if I talk about this cell, the maximum number is 30, so I talk about 30. Similarly, it is like maximum number is 112, I will talk about 112 like that. Okay. So all these 16 pixels has now reduced to 4 pixels. Okay. So now my further processing has to deal with a reduced dimension, not really a very large number of values. Okay. And that has helped in reducing the final layer size essentially. You know that the final layer is still based on backpropagation errors. So that reducing all these will actually help us in reducing the dimension of the final layer essentially. So that is a very useful feature for reducing the dimension. And remember, these even though you are talking about the simple operators, right? Convolution itself is just a kind of inner product sort of operator. You just multiply everything, take a summation, and there you're talking about just taking out the maximum number or do some sort of averaging. That means you add up all these numbers and divide by 4, add up all these numbers, divide by 4 here, like that. So if you do that simple operator, eventually it actually leads to a lot of image processing results. Right? So both of these, for example, have noise suppression characteristics, and then max pooling actually helps you that in a very big way. Okay? So it actually talks about enhanced things, image enhancement sort of thing. Right? It gives the largest value. And as suppose I have to go back and then attribute the features. I have only these numbers, and I have to attribute the features backward. Then how do I do it? Right? So that the whole idea here is, well, I will just put these numbers back everywhere. Okay? Instead of all these things, I will talk about 20, 20, 20 everywhere. So if you see that way, backward processing in that sense, basically, right? Suddenly the distribution of numbers, what happened here in a very different ways, the distribution will become very sharp, right? You can see only all these values will be 20, all these will be 30, all these 112, all the 37. So we can see the image contraction, the image enhancement happens in a very big way. Rest of the things are gone, basically, right? So that is where this kind of noise suppression features has been put into that. All right. So again, advantages of pooling, I've already told you. Spatial size reduction, it leads to decrease in the size, so essentially decreases the computational power required as well. And then noise suppression, I've already told you about that. And then it is capable of extracting dominant phases, which are rotational and positional invariant. So because what happens again, if I just talk about that, if you assign all the numbers 20, then it doesn't really matter where it is located, right? So this 8, suppose right now if 8 changes here and 20 comes here, there's a different value. But if everything is 20, it really doesn't matter which one you put here, everything is same anyway. Okay? So that is why this brings in certain invariant features, which is actually good for the thing, I mean, which is good for the training processes. Okay? So it gives you rotational and positional invariant features. All right, so then finally the concept of image flattening. So whatever the last segments are accumulated, all that it does is just accumulates like a vector. This matrix, what you see, 1 1 1 1 0, then 4 to 1, 4 to 1, then 0 to 1, and then 0 to 1. So a matrix, what is resulting matrix eventually is converted to back to a vector, so that this vector can be eventually fed to the last layer of the neural network system. Right? So this is kind of a nutshell of what is happening in the convolutional neural network. So you've got a input volume, which can be large. Then there are these convolution layers. Then there are this. I mean, eventually we'll talk about some 1 or 2 hidden layers, which are actually done in the way that classical feed-forward networks are actually were done before. Okay? But there is also an innovation out there. I mean, there are 2 innovations. One is the usage of activation function, which is very different. And then the second one is stochastic gradient-based optimization. All right, so this is the nutshell, and this you talk about kind of not in a hand-picked way, but the automatic way of doing that. There will be convolution layers, which will extract this lower level, then followed by middle level, followed by high level, and then you talk about a convolutional trainable classifier sort of thing. And this classifier will automatically, because the final image is already tagged basically, right? Final image, the training data set will contain all that. So it will be trained with respect to these kind of final details to a particular thing. So the chance of error will also become minimal. So this is, but remember the computer is a bit larger, right? So because several layers have come in and several, these filters you have to try out, and something that is not working you have to discard, something working you have to keep, lots of permutation combination you think about. So it's a combination of gradient optimization and non-gradient optimization in some sense. So this is why it takes a lot of time to train the database. But good thing is it doesn't require any expert. It just requires a limited amount of level data set, and after that the theater level training. Again, to summarize, the initial layers learn very low level features like adjust corners, small textures. Intermediate layers learn medium level features like eyes, nose, and things like that. And then deep layer eventually leads to high level features like face, cars, right? So this is what we talk about. And so again, to summarize, what all we talked about, we talked about filters, we talked about downsampling, we talked about pooling, things like that. And downsampling need not be only pooling. There are other operations as well, like you discard the non-region of interest. Right? Talk about a region of interest here. So this looks too very big large, and I don't need that. I need a small portion of that. So things can be gone. Right. So this is called downsampling. So you reduce the zone of interest to a good place. Then max pooling, we talked about it, and then eventually what is left out is ReLU function. Right. So let's talk a little bit of that also. All right, so what is ReLU function? Now go back to a little bit of initial portion, and we talk several activation functions. So, and one very popular activation functions that were used in the conventional feed-forward neural network is something called sigmoid function. And it looks like that, a function is of this form. You can attach various weights. So instead of -x, you can talk about -5x, -10x, whatever it is. It will take a different shape. The rate of change near zero will be very sharp or flattened and things like that. But then the eventually thing is it is not going to be zero ever. It's going to be zero at minus infinity, or it's going to be some +1 at plus infinity. So it is just kind of not really very good in a lot of applications because of this asymptotic behavior in what we call in control theory. Right? It is going to zero, but it's going to zero at minus infinity. So that is really not good because the numbers will be very small, very small, very small. But then these small numbers are carried forward as non-zero things basically. So then there's something called not really the associated neuron is not really contributing much, but you cannot classify them as not contributing much. Right? So for doing that, you really need zero numbers, right? Zero output basically. So that is where things are one side of the concern. The other side is even in the positive side, it was saturating to 1. That means it is actually a nonlinear function. So taking me towards the saturation level very soon. If my values are large and large, I will not see distinct outputs. Everything will produce almost like the same number sort of. So I will not be having this classifier sort of application. It is not really good idea because all of them will be classified to single category sort of things. So that because of these two reasons, people thought about something different, and that is where the concept of ReLU came in, like linear unit. Extremely simple again. It talks about something like y equal to x or f of x equal to x in the right hand side and 0 on the other side. It can be coded very simply by taking this maximum operation. Okay. If anything negative, then the maximum happens to be 0, so it will all output to 0. Anything positive side, the same value will be output. That's all it's. Okay. Instead of a simple linear line, you talk about negative side all 0, positive side as it is. So the beauty is whatever zeros happen, it will happen for a continuous period, and then those things can be kind of discarded and all that. So it will help us identify which are not really contributing to the output essentially. And that is a lot of good cases to speak. So what are the advantages you're talking about? Of course, very simple and efficient. This is just a coding of simple function max operator, maximum operation. And then there is this concept of vanishing gradient, right? When your number becomes away and away from zero, either this way or that way, your gradient value happens to be close to zero, right? And that problem is suddenly avoided because here it will be gradient will be always 1 on the right hand side and it is always 0 on the left hand side for zero. So that slowly vanishing gradient problem and all is avoided here. So also it actually helps on in something called representational sparsity. That's what I just talked about, right? Whenever there is a small value and things like that, it actually gives you 0 value. Okay, it doesn't give you a small value in the negative x-axis. It actually directly gives you 0 value. So negative number anyway it was small, okay, earlier, but now it is truly 0. So you can now talk about which neurons do not really contribute much. So those, it will help you in downsizing the network and all that. And then of course it leads to faster conversions as well. So these are typical functions, typical advantages of ReLU function. And it looks very simple, but somebody has to really think deeper into that to get into this function. But also remember this so-called advantages, nothing is a free lunch. So it comes with some sort of a drawback. And what is the drawback? The dying ReLU problem, right? So what happens here is for a large number of times, suppose it remains negative for a large amount of training cycle, then it never produces any value, right? So essentially, you can think of that neuron has died, right? That is not producing any output at all. So that is what is called as the dying ReLU problem, and so the ReLU neuron becomes inactive, and only output is 0 from any input that you put. Okay. Of course, in the negative side. Now, to avoid that problem, people have thought about a little bit modification of the ReLU function as well. And so there are some innovations here. So, well, one is leaky ReLU. So don't talk about pure 0 here, but you talk about y equal to x on the left hand side. And something like, well, a little bit of number will come up in the other side. Okay, so this is also straight line up to 0, but other side is not pure 0. Depending on the coefficient value that you take, it will be small value of that will keep on going. That's a leaky ReLU or something somebody called parametric ReLU and all that. And then after this leaky ReLU, there are other concepts, and the other concept talks about exponential linear unit or LU function. So some people call E-ReLU, and okay, so but I think this is more kind of appropriate. So exponential linear unit. So essentially, you talk about linear in the positive side, but you put a very saturating linear function sort of thing on the other side. Very quickly, it will saturate to a very small. So the problem with this number is it slowly becomes larger and larger and larger and larger and larger. Right? It keeps on growing in the negative side. Even though initially the numbers will be slow, the later on the numbers will be very large, depending on how far you are from 0 axis to the negative side. So to avoid that, you talk about a saturating function in the left hand side. And on top of that, if you talk about this alpha is 1, then you can ensure that there is a derivative continuity at x equal to 0. Right? If you talk about value continuity is anywhere there. At x equal to 0, both are 0. The function continuity is anywhere there in all this. This is piecewise continuous. Now it becomes also kind of piecewise continuous. But in addition to that, if you take alpha equal to 1, then obviously if you take derivative of that, so that derivative also turns out to be when e to the power 0, which is actually 1 basically. So essentially derivative continuity is also maintained. That is not its nice property in the gradient optimization techniques that you are going to use. Now, another one somebody thought about, well, this is really not a good idea. I will like to have this number very close to 0 instead. And then they talked about sign ReLU. Okay. So if you see that the value is 1, but the negative side is very close to 0, but really not 0 in that sense. There is a little bit amount of oscillation. If you zoom this one, you see a small variation of the oscillation. And this can be modeled in this kind of a function. If Z is positive, then of course you take Z, but if it is negative, then you multiply this sin z minus cos z whole multiplied by this small value epsilon. So this small epsilon value is going to kind of bound it around this 0 value and all that. But remember, derivative is not really 0 for that. Derivative will have its own meaning, own numbers. So we have various modified values, modified leaky ReLU and leaky ReLU, LU, sin ReLU, or sort of things are available. And then, okay, somebody thought about, well, what about the positive side of the story? If you talk about negative side of the x-axis can go very far, and then you have a problem. Now, positive side of x-axis, if I go very far, this also goes to infinity. This is an unbounded functionality, right? The linear function is going to be unbounded. So to rectify that problem, earlier it was kind of limited to value 1 kind of asymptotically. Instead of that, very easy fix. Again, we talk about, well, I will just talk about value 6, value 10, value 600, value 800, whatever it is. And eventually that number is going to saturate at that value. It is pure value. But in the right hand side, I am concentrating now. I will saturate it at whatever desired number I want. So these are various permutations, various combinations you put out about. So you can select whatever you want and then experiment whatever you do. You can have a combination of these two also, right? You can, instead of ReLU 6, you can talk about LU 6. Right? So in the right hand side, it will remain same, but the left hand side, it will become a kind of this LU function. Probably, I will probably rather recommend that and fix this number to a reasonably high number, so that for a large number of large x values, we still have a kind of linear function. Not give you saturated values. All right. So essentially, we talk about, well, some summary sense. What has happened here actually in a nutshell? So if you think about this, new algorithms and tricks for training deep neural networks. Essentially, there is a data augmentation. So multiple increase by cropping, clipping, all sort of things you can do. Rotation, cropping. When you take a picture, crop it out, and then that becomes another picture. You kind of rotate it out, flip it out. Right becomes left, left becomes right. That is still the same person. So we can talk about tagging that way. So you can generate a lot of data augmentation. And then you are ready for the training exercise. Then new activation function, ReLU, the rectified linear unit. Then there are a lot of these regularization methods are available. Essentially, you have to come out of this local minimum and things like that. So what is the idea is like just 50% of the neurons in the last layers where you actually use this gradient-based optimization are switched off. That means you don't update. Okay, whatever is there, your gradient value tells something, but you don't update, just remain there. You will update in the next cycle or something. Okay? So that process helps you avoiding this local minimum. This process is called regularization. And there are a lot of these initialization methods also available. Remember, all that so far we have been talking about training, but training is essentially updating the weights. But then how do you start with the weights, right? You have to start with some sort of initial weights. And that is where people have proposed this randomized algorithms and all that. So that it will roughly kind of do the numbers out, predict the outputs not very far from what is supposed to be. So those are a lot of these initialization methods have also kind of appeared. And of course, you can use various optimization methods. And as I keep on telling, the stochastic gradient method is probably the latest one, which avoids this local minimum problem to a great extent because of its randomness behavior. All right, you can start studying more on that in the literature. Now that kind of finishes our explanation of understanding of CNN. Now, how do you kind of implement all these whatever you talked about? Right, there are so many concepts that we talked about. So if everybody starts sitting there and then trying to explore their own way, it's not going to be a very easy task. And it is probably not, good thing is it is not very classified anymore. Many of these things are available in the public domain already. So these are some of the things that are available. And historically, if you see, it is not really, some new initial concept getting started in this 1998 sort of thing. But then all these innovations were not available. Like we talked about like ReLU function and stochastic gradient, all these were not available. So that's not really a major milestone. The major milestone happened during AlexNet and this Alexa and all that we talked about, and so that kind of a thing. So that is where the 2011-12 it started appearing in the literature. And then there are this VGG class of CNN. Then there is ResNet, the exception, Inception version 1, 2, 3, 4. And then various combination of that. Eventually, there is something very specific to mobile phone applications and all that called the mobile network. So you see the performance-wise, some application, I don't know what application it is, but I've taken from some arbitrary information. And then in that application, if you talk about accuracy part of it, so these are some of these accuracy levels. So probably the Inception ResNet V2 performs very, very well. Comparatively a lot better. But then if you really talk about the size of the network, size of the tunable quantity, so that's the parameter sort of thing, that actually dictates how much faster you can train a network. You can see the number of pre-parameters are much lesser in the mobile network. So probably if you really want to start something, then I will probably recommend to start with the mobile net sort of thing. And it's also a kind of a recent development compared to the other ones. So what is this various architecture that we talked about in the rest of the things? So these are some concepts that we studied, but suppose you take one of that or a couple of that, then what are the structures that you are talking? How much is the realistic size and all that? Right? So that's the natural question that pops up. So let us talk a little bit about that as well. So I've taken this from a different website. So these are some of these notations used. If somebody talks about a circle with a T, that means a tangent hyperbolic function. Circle with a R, that means ReLU function, like that, right? So if it is a dense layer, it is given by blue. It is the module layer. These are some of the sign conventions that is used in the subsequent to these slides. All right. So if there is a square bracket, then there are multiple layers there. Actually. So that is repeated layers or modules and things like that. So using this sign convention, let us talk about some realistic things. So this is the LeNet 5, that 1998 sort of thing. Even that far back, somebody talked about kind of 60,000 parameters. It's a relatively daunting figure. 60,000 parameters when you talk about in a conventional way of training, obviously things cannot work out. But they did it some innovations at that point of time itself. They started working out, and then it has already become kind of a standard template to compare or start with. And remember, 60,000 looks very big to us, but actually it happens to be very small. Okay. Then what is big and all that? We'll talk about that. Okay. So remember, this is the concept of 10 hyperbolic.